and thank you, IGS, for giving me this opportunity just to give a little bit more detailed introduction of myself. I'm Sonam Rinzin, and I'm currently undergoing my PhD studies at Newcastle University, United Kingdom. For my PhD, I focus on coupling, combining hazard mapping with the downstream exposure and vulnerability data using agent-based model. But today I'm going to present one of my PhD chapter that is titled as Advancing Glacial Lake Hazard and Risk Assessment in Bhutan through Hydrodynamic Flood Mapping and Exposure Analysis. This paper has been just published in Nature Hazard and Earth System Sciences yesterday. So uh, I will take you through this work in next 20 minutes. Okay, firstly, uh, this is a Bhutan map showing a distribution of glacial lakes and glacier in the upstream basins and distributions of infrastructures and other properties in the downstream area. In Bhutan, there are about 5,800, around 1,580 glaciers, which cover about 4% of the country's total land cover. And the recent studies have reported that about 524 glacier has become extinct within the last decade. And as this glacier retreat, they leave some favorable topography that leads to the formation of glacial lakes. And in Bhutan, there are about currently, as of 2020, around 2,500 glacial lakes that cover about 150 kilometers square. That is actually about 500 in terms of number increase from 1960s and about 26 kilometers square area increase compared to what has been there in 1960s. Now, uh, now Bhutan has very rugged topography, and our only the fertile lands are or arable lands that are suitable for agriculture and infrastructure development are located around the rivers, around glacier-fed rivers. That's why Bhutan's main source of energy and economy is hydropower, which is actually driven by the glacier-fed rivers. And also, more than 60% of the people depend on agriculture for their livelihood, which is again indirectly or directly dependent on those glacier-fed rivers. And within these floodplains, Bhutan's built-up area has increased by about 194%. Now, these glacier lakes are some of these glacier lakes are susceptible to producing glove. So this sketch I have taken from Zhang and others study, which is published in Nature uh, Art and Environment Review, something. So here we can see that glacier lakes are formed on the topography left by the retreating glaciers. As glacier retreat, they the mountains which are once supported by the glaciers become unstable because they are now no more supported by the glaciers. And these mountains can produce mass movement, catastrophic mass movement that can enter into the lake. And likewise, there are many things going on in these mountain slopes. For example, permafrost are thawing because of climate change, and this also makes them more susceptible to produce mass movement that can enter into lakes. But it is not only that. Now, extreme weather events like extreme precipitations and uh, and extreme temperatures are also increasing, and this will also lead to increased runoff, which can also overwhelm the moraine, damming the lakes. And likewise, the moraine contain ice, some moraine contain ice core, and which are also melting because of climate change. And this also destabilize the moraine, damming the lakes. Now, all these conditions makes glacial lakes susceptible to producing glacial lake outburst flood. But that's the this it is not only about the susceptibility of the glacial lakes to produce glacial lake outburst flood. More important thing is there are people living downstream of those glacier lakes, and when this flood originating from the glacier lakes interact with the downstream elements, that is where it become dangerous and risky to the downstream settlements. In fact, around the world, uh, thousands of glacial lake outburst floods have already occurred. The number might be even more, but recent documentation says there are about uh, 4,000, more than 4,000 glacial lake outburst flood has already occurred. Out of this, more than 600 events have occurred in high mountain Asia. In high mountain Asia, about 50% of them are sourced from moraine dam lakes. Now, these moraine dam lakes are particular growth from moraine dam lakes are particularly concerning because they are the growth events which has caused most damages in the downstream. This is partly because they are located relatively near to the settlement compared to the other types of lakes like superglacial ponds. And in Bhutan alone, they have recorded, past studies have recorded about 24 globe events. Out of that, the Lugiso events in 1994 was the most devastating one, which left about more than 20 people killed and damages hundreds of buildings downstream. Now, these globes are very devastating. That is because when the glacial lake outburst flood occurs, it can unleash uh, hundreds, tens of millions of cubic meter of water with very high peak discharge. And as this flood water propagate further downstream through rugged mountain terrain, they can erode riverbed, and then it can further multiply the flow. So as a result, it become very destructive in the downstream settlement when the flood reach downstream settlements. For example, these are the satellite image taken before and after the South 2023 catastrophic South Lona Globe events. You can clearly see the extent of erosion and devastation that was left by the 2023 event of South Lona Lake. And now, the one thing that we have to understand is what it really matters is not only the globe magnitude itself, but the downstream settlement characteristics that met downstream settlement characteristics, the location of downstream settlements and the performance of the structures all determine ultimate damage and destruction that occurs during the glacial lake outburst flood. For example, in case of uh, South Lona events in 2023, you can clearly see here the most of the damages have occurred between uh, 200 to about 400 kilometer downstream the lake, downstream of the lake. That is because the settlements are mostly concentrated within this region. Now, this gives us a very strong rationale why downstream elements is more important, why it is important. So to this end, now this study produced glacial lake hazard map for each glacial lake in Bhutan. But here our limitation is we selected glacial lakes which are above 0.05 kilometers square, and we map all the downstream exposed element within the inundation boundary, and then assess the risks associated with each glacial lakes and each downstream communities, and then provided new and updated ranking for glacial lakes based on their flood magnitude and downstream settlement characteristics. This is a summary of method. So this is very high level summary. So if any one of you wants to know more detail, then I'm happy to discuss during the question and answer session. So we have selected 278. That is again based on the area criteria we set. But having said mentioned that, we acknowledge that now it is increasingly these small glacial lakes can produce devastating glacial lakes flood also. Now we use the volume and peak flow data from each glacial lake, which were calculated using empirical equations and generated hydrograph. And this hydrograph was used as an input into the HACRAS 2D model, and then produce a hazard mapping for each glacial lake. Now, within this inundation boundary, we mapped exposed element, and for the exposed element, for each building, we determine vulnerability using population and census data. And finally, we calculated glove risks as a function of exposure, vulnerability, and hazard. These are some of the results. This map shows distribution of high hazard glacial lakes. So Tortormitso was identified as a very high hazard lakes. That is because it is the largest glacial lakes in Bhutan, but it is our identification is not only because it is the largest, it is also because it can impact thousands of buildings located downstream with very high magnitude flood. Likewise, we identify 5 other lakes as high hazard lakes located across the 3 basins within river basins in Bhutan, and 22 were identified as moderate hazard. Now, this classification is mainly for the visual purpose. Alternatively, we have provided the ranking for each glacial lakes and number of buildings affected by each glacial lakes. That is because our classification might be also biased. So if, for example, the policymakers are interested to just look at the number of buildings affected by affected by the glacial lake outburst flood from particular lake, so they can also consider our data. Most noticeably, we identified 3 lakes, which 3 lakes as high hazard lakes, which were not previously identified as high hazard or high risk lakes. And this is important because they are located in the upstream in the area where like in the basins downstream of which have thousands of buildings. This is the distribution of downstream Gulf rigs. Here also, we have identified five downstream settlement as high Gulf rigs settlements. Here we call them as LGU, that is local government unit or local government administrative unit. And in this here also, for the downstream settlement also, we have identified some of the area which are previously unknown or not monitored for Gulf risks. For example, Parota, which is most populated town after our capital city, and where the international airport is located. So and if you look at this figure at the right panel, you can clearly see like where in the area where we have identified as high Gulf risks, there are lots of buildings. And as mentioned earlier, our Gulf risk identification is by considering both magnitude of Gulf from the lake and the downstream exposure. For example, in the panel A, we have for the downstream Gulf risks, we measure Gulf magnitude in terms of depth velocity, the depth velocity that affects the building. It's a median depth velocity across all buildings that are affected in particular downstream area, and number of buildings. So here, for example, places like Lunana, they are around hundreds of buildings are affected, but it is fairly affected by uh, uh, growth of it is affected by more glacialic outburst flood sourced from many glacial lakes. And likewise, Chekor, for example, here, which is the number one high Gulf risks downstream area we identified, it can be affected by uh, like uh, more than 10 glacial lakes, and about 200 buildings can be also affected. And likewise, in the right panel, we measure the Gulf magnitude in terms of peak discharge from each lakes and number of buildings for the exposure. Here too, we can see like clearly the lake 130 stand out. That is because about thousands of buildings are affected, and it can produce very large glacial lake outburst flood. So these are some of the conclusion from our studies. So we here emphasize the importance of incorporating flood mapping and downstream exposure for defining Gulf risks. And this we consider this as important for strengthening Gulf risk mitigation strategies in Bhutan, particularly strengthening the existing early warning system, expanding their coverage to newly identified high-risk area. Now glacial lakes are changing, and this changing rapidly, and that means the hazard from these lakes will also evolve. So we are looking forward to update the hazard mapping in the future, and we are hosting this hazard map in our website here. And and also like for those area where we identified as high risk area, so we recommend conducting in-depth study using the field-based data and high resolution modeling. uh thank you all for taking your time. So that's all. And then yeah, if you have any question answer, so happy to chat during the question and answer session. uh,
Awesome. Thank you, Sonam, for that really nice talk. And next we have Sonam's colleague, Alex Hyde, also from Newcastle University, presenting next. So please take it away, Alex.
Cool, let's get my screen shared here. Here we go. Can you all see that all right? Is that working okay?
Yeah, that looks good.
Brilliant. So yeah, thank you for that, Son. I think that leads quite well onto this. Once we were looking at Gloff risk time, we were also interested in understanding how the lakes themselves, particularly in this Lunana region where there's a big Gloff risk, were affecting glacier retreat and driving velocity. So we were interested in understanding monthly and seasonal resolution how ice velocity changes in Lunana were driving lake expansion. In terms of seasonality, and then we took this data, then expanded it across the rest of the Himalayas, and then compared that with the retreats. So that's what I'm going to try and cover today. Is that moving? Okay, so the standard model of seasonal ice velocity, as many of you will know, is driven by change in meltwater runoff throughout the year. So generally, we see acceleration in the spring and early summer season when we're getting a peak in basal water pressure due to water draining into inefficient cavity systems, driving up water pressure. This then results in the channels becoming more efficient, leading to a reduction in basal water pressure over time, and then reduction in ice velocity as the melt season progresses, usually leading to a recovery of the ice velocity later in the winter as the channels reduce in size again. Lake formation can obviously have a big impact on ice velocity. It reduces basal friction near the terminus by undercutting the glacier, leading to flotation as well, which results in big accelerations towards the terminus, and then calving, of course, as well, which is associated with greater rates of retreat. Generally observed in marine terminating settings where there's been a lot of study done. There's been a lot less study done in the Himalayas and alpine glaciers in general in terms of how lake formation affects glacier retreat. So we're really interested in this Lunana region. This glacier Thorthorn in particular underwent very rapid retreat around 2021, 2022 when a large ice tongue disintegrated in a matter of a few days. So we want to see whether there was a velocity signal that could be used to describe that retreat and why it happened, and compare it to its neighbouring glaciers, understand why those glaciers haven't undergone retreat in a similar manner. There's a few shots there of the field site. It's a very impressive location, huge moraines, and yeah, as it's Himalayas, everything's on a huge scale. So this glacier Thorthormi, as I mentioned, had this very large ice tongue, a couple of kilometres long, and in 2019, a large landslide event near the icefall area. I don't know if you can see my mouse in here, probably not, but just towards the icefall area triggered a small gloff, which led to the breakup of the existing ice tongue. That then suddenly reformed by spring 2022, and then it rapidly disintegrated towards the end of the year. So what we did, we used planet imagery, which is very high resolution imagery. It has daily temporal resolution. This allowed us to capture imagery during the monsoon season on a rare few cloudless days, and we're able to build a really good monthly velocity time series from 2017 till 2024. And this allowed us to capture those short-term variations in ice velocity that were linked to these large calving and breakup events that we saw at Thorthormi. We utilised this software called Glacier Image Velocimetry, developed by Max van Wyk de Vries at Cambridge University. This has got a really cool function called temporal oversampling, which allows us to compare multiple non-consecutive image pairs in order to build a really good monthly average. A lot of people in the past had challenges using Planescope imagery for ice velocity because generally the ortho rectification quality is quite poor. So especially on the mountain slopes, they tend to distort the images a little bit. And when you're doing feature tracking on the glaciers, that tends to upset the quality of velocity outputs between individual image pairs. But when we're averaging over multiple image pairs per month, we're seeing a lot better velocity time series. As you can see, the monsoon itself really reduces the number of images you can capture throughout the year, particularly in the eastern Himalaya, where there's a long and extended monsoon. As you can see, you don't really get many images for Sentinel or Landsat. So Planescope does allow you to get a little bit of imagery during summer months, even though it's still quite limited. So in terms of our results, we found that the velocities in the region varied massively between glaciers. So you can see we've got velocities varying from 10 to 400 meters a year. And what's interesting is that we found a very strong signal between acceleration of Thorthormi and that eventual breakup in 2022, 2021. Here the glaciers split into a lower and upper region, the red showing the lower region, which is basically the ice tongue of Thorthormi here. You can see it had velocities reaching close to about 450 meters a year, which is exceptional for the Himalayas, preceding that breakup event. Whereas the upper region of Thorthormi was showing consistent deceleration over the same period, which is generally what we expect for Himalayan glaciers, where we're seeing a lot of melting, thinning of the glaciers and reducing driving stresses. So across Himalayas, deceleration has been observed generally. As you'll see in the study, this, where we've done more broadly on the Himalayas, contradicts that, and we're seeing a lot of acceleration towards the termini of a lot of glaciers in the region. So moving on, we wanted to look at how the large lakes, larger glaciers, so greater than 2 kilometers squared, are being affected by proglacial lake development. So we use this new lake classification method developed by Armstrong and Balch a couple of years ago to narrow down our study area to just these level 1 glaciers where we have over 50% of the terminus in contact with the lake. Generally, they're large lakes, and you can assume that the lakes having definitive impact on glacier behaviour. We also mapped out level 2 glaciers in the region where the lakes might be having a bit of effect on the glacier, but it's not necessarily sure. And level 3 glaciers where they're quite small lakes in contact with the ice. You can see in these images here, very minimal contact. But it could be relevant to glacier behaviour, but unlikely to be so important. So looking at the distribution of level 1 lake terminated glaciers, you can see that most are located towards the eastern and central Himalayas. We have a few in the west and the central west and far west. But the western Himalaya itself is actually quite limited in terms of the number of large level 1 lake terminating glaciers. There might be some smaller ones, but we excluded those from this study. But generally, they're mostly towards the east and far east. The glaciers in the far east, in particular, are a lot larger than those in the far west. So you compare that, we had about 83 glaciers in total, about 93 for level 2, and 122 for level 3. And actually, this map just beyond the Himalayas, so Himalayas as well. But we restricted the studies to the Himalayas in the end. So you can see we've got a massive range of ice velocities across this whole data set. But there's some clear trends here, particularly between regions. Far eastern Himalaya has much higher velocities than the central eastern region in particular. Velocities around 73 meters per year for the far east on average, compared to about 22, 23 in the central east. And again, the Lunana glaciers in the eastern region, that's F here on this plot, stand out as well. See Thorthormi with its massive range of ice velocities, a real outlier in Himalayas, as well as those other Lunana glaciers, Betram and Lugay, are also really fast flowing compared to glaciers in Himalaya generally. So there you go, you can see those outliers again. The Lunana glaciers are right towards the right end of this scale. This is just mean ice velocity. You can see the range of whole Himalayas with some glaciers flowing as low as 10 meters a year on average, or lower than that. So it's a big range of ice velocities, and it just shows the massive amount of heterogeneity across the region. So we look at the trends across the Himalayas, we can see, again, there's a big variability in the magnitude of ice velocity, seasonal ice velocity variability between years. The Far East and the East Himalaya, again, you can see huge seasonal variability in ice velocity here, whereas the Central Eastern regions, Central Himalaya, are much more subdued in the magnitude of seasonal velocity swings you see each year. And above the ELA and below the ELA, we don't see a huge difference in ice velocity on average, but the trend below the ELA suggests, above the ELA we see a much greater trend for deceleration above the ELA than we do below the ELA. The strongest trend is obviously seen here is the far west, where we've got about 10 meter a year decrease in ice velocity on average, compared to below the LA central western region, where we're actually seeing some acceleration in that area. But that's the only region in Himalayas where we are seeing acceleration on average. What's really interesting is when you average all that data together, we discovered quite a interesting trend in terms of the divergence almost between ice velocities above the ELA and below the ELA in the lake terminating setting. So pre-2021, on average, ice velocities above the LA were flowing faster than they were below the LA. And that's generally because we had steeper gradients above the LA, where below the LA we've got a lot of low gradient ice tongues, which are generally quite slow flowing. But we're starting to see a transition now where on average these ice velocities are flowing faster below the LA than above the LA. I think that's quite a significant indicator in terms of what might be going on towards the terminus. We've got those lakes developing, resulting in those reduced basal drag, flotation and acceleration in that region. Whereas above the LA, we are getting net thinning, and that is driving a stronger decelerating trend. This trend is actually visible pretty much across all regions here. Less so in the Far East, interestingly. And we've got a little bit of a theory going on that might be because the lakes in that region are actually more mature, and the glaciers have had lakes there for quite a long time, and they've sort of retreated enough to reach an equilibrium point where we're no longer seeing acceleration below the Himalaya. With some regions like the central Himalaya, we're actually starting to see much more pronounced acceleration, particularly post 2021, 2022. And that seems to be quite uniform timing across here. And we don't seem to see a correlation with temperature or precipitation or any climatic changes occurring around that year. But we do see a strong shift in velocity and ice dynamics around that time. So looking across, this is a sort of a whole glacier plot for every glacier in the study. There's 76 of them in total that we narrowed it down to. And you can see there's a massive amount of variability, both in terms of the interannual swings in velocity changes between glaciers. With a lot of glaciers showing very little change between years, less than 5% annual velocity change, whereas some glaciers were seeing over 15% increase or decrease in velocity between years. When we look at the average of this, again, 2021 stands out as a unique year with net positive change across all glaciers on average, whereas all the other years have generally had a negative trend. This is also true above the LA flat year. We've got a 2% increase in 2021, whereas the other years have been negative, and increasingly negative in the last couple of years, 2023 and 2024. Obviously, this is quite a short timescale, so it's difficult to draw out any strong conclusions from that. And again, above the LA, we've seen acceleration in 2021 and 2022, and negative velocity trends in the last few years. So if we look at seasonality itself and the timing of the peak in velocity, so when we're seeing that seasonal peaks, which we typically expect to occur in spring and summer, there's a lot of heterogeneity again in this data here. So most glaciers generally below the LA are peaking in the summer or spring. Then when we look to the right of this graph, this Sankey plot here, we see that most of them are actually peaking in autumn above the LA. Generally, that's sort of what we'd expect. However, there are a lot of glaciers that do peak in winter, both above and below the LA, which is quite surprising. It's not unknown as the case, but it's interesting that there are some that peak above the LA in winter, or below the LA in winter, and then above the LA they peak in spring. So it's quite interesting dynamics going on there. And you see this varies a lot between years as well. So in 2017, maybe 20% of the glaciers in the data set had their peak velocities occurring in the winter, whereas in 2023, above the LA, that was down to 10%. So it varies quite a lot between years. So that's just something interesting to share. And when you look at all the glaciers data, again, you see a lot of variability between glaciers and also interannually. So some glaciers, like Yano Glacier here in the central Himalaya, you can see consistent peak in annual velocity occurring in the fall/autumn season. Whereas other glaciers, you have a huge amount of variability between years. We've got some that one year they'll peak in the winter, and then next year they'll peak in the spring, then the summer, then the autumn. So a massive variability. And this is just this plot here is a whole glacier plot. So both the LA and below the LA. And you can see there's no clear trend necessarily, but you can see the average there. And above the LA, we see that has generally shifted to being summer, predominantly summer, whereas in the early first few years of the study, they were peaking in the winter and autumn season or fall. Where below the LA, they've consistently been peaking in the spring and summer. Again, that's maybe shifting towards the spring. So that could be indicative of just a warming trend in general in the Himalayas, driving earlier velocity peaks in the season in later Himalayas classes above and below the LA. So when we look at the overall controls of ice velocity, we did a Pearson correlation between a variety of topographic, geographic controls, and also some climatological controls that were derived from ERA5 for analysis data at monthly resolution. Unsurprisingly, we found that ice thickness is a predominant control on medium ice velocity, so thicker glaciers have higher driving stresses, so that's not surprising. We also found that steeper glaciers tended to have ice velocities that peaked earlier in the year, which is quite interesting as well. North-facing glaciers tend to flow slower on average, and they also tend to have weaker seasonal cycles as well. Monthly precipitation showed a correlation with peak months, so glaciers with wetter climates reach peak velocity earlier in the year in general. When you look at the sensitivity between velocity and temperature on an annual scale, we see the glaciers that are dynamically sensitive to annual change in ice velocity, annual change in temperature, are actually speeding up. So that's quite interesting when you look across the whole glacier. We actually found a lot of other stronger correlations below the ELA, however. So it's just to click out for you there. I'm not going to see it. So there are a lot of interesting relationships below the ELA. In particular, we found that glaciers with steeper slopes have a lot stronger seasonal signal in terms of seasonal magnitude and variability and amplitude. Whereas again, they tend to peak lower in the year. So a lot of stats to go through here, but yeah, let's touch on a few other interesting ones. Again, we're seeing thicker glaciers flowing faster, and some similar correlations with the whole glacier area. But what's very interesting is when we look at the temperature sensitivities, is that we see that glaciers sensitive to monthly changes in ice velocity tend to be much more harmonious in their interannual signals. So we tend to see much more consistent monthly changes when we see strong relationship with temperature, as you'd expect. But on an annual scale, looking at temperature trends, we can see that glaciers sensitive to interannual changes in precipitation are decelerating at a higher rate than those that are less sensitive to interannual changes in precipitation, which is quite interesting. Whereas glaciers that are also tightly coupled to internal changes in temperature, they're actually speeding up at a higher rate than those that are less sensitive. So those are a few of the interesting controls, and I can discuss some of the others if I have a bit more time later, but I'll try and get through this without over time. So moving on to the next bit now is we also looked at retreat on a monthly scale as well for those glaciers, and we use that same PlanetScope data set to map glacier terminus change using the box method. And once again, it's a really heterogeneous picture across the whole Himalayas. So you've got some glaciers showing a very consistent rate of retreat, some which have a very stepped rate of retreat, where it's very stable and then suddenly starts retreating very rapidly and then stabilizes again. Others which have a seasonal retreat pattern of advance and retreat going between years. And then a few glaciers and data which were actually advancing over this study period. So we look at them together, we see on average, glaciers in the Far East retreated the most during this period, whereas glaciers in the Far West showed the lowest rates of retreat. And this is consistent between the trends, so you can see the trends in both the decadal trends. We've got on average about 200 meters of retreat per decade, averaging this data out compared to over 400 meters in the Far East. And just looking across data set, you can see that once again, for Thormy, that Lunai Glacier is a big outlier in this data set with the greatest rate of retreat per year, on average 120 meters per year, which is obviously very high compared to a few glaciers in this data set that were advancing over this period by a little bit or showing little change. But generally, across the data set, we've seen net retreat. And like peaks in ice velocity, we see most of the retreat occurring in the spring and summer season, generally towards the later summer. That retreat period is longest in the Far East, there between March and October, whereas in the central western region, it's a much shorter retreat period. Generally in the central west region, that we see much generally finds the middle of the summer, June to September. So we look at the controls on retreat. What was interesting to find that glacier geometry is actually the most significant control here. Ice thickness in particular, and terminus width generally is the biggest indicator of retreat rates. So glaciers with wider termini are retreating faster, and thicker glaciers are also retreating faster. So we also see that ice velocity is an important control on retreat, not on overall retreat rates, but when the glaciers flowing faster, the higher retreat rate each year on average. But the fast flowing glaciers have a trend overall that's actually slowing down, which is interesting. We see a negative relationship with precipitation, so glaciers receiving glaciers receiving more precipitation are actually retreating faster, which is quite interesting. I don't know if that's a relationship with ice velocity, but we don't see a relationship between the net change over the same period and ice velocity. So it'll be interesting whether precipitation is driving a retreat in another mechanism other than increasing ice velocity through contributing water to the bed. So that was one interesting statistic that came up out of this. But what we do find is that velocity acceleration actually corresponds with accelerating retreat. But conversely, the glaciers with the increasing velocities are actually showing much lower rates of annual retreat. So that's quite an interesting statistic. I think it's something potentially to do with that idea that glaciers in the Far East have actually reached maturity, so they're slowing down, and their rates of retreat potentially also slowing down. But glaciers that with increasing velocity in the central west, in the Himalayas, central Himalayas, where the lakes are just starting to form, currently have quite low rates of retreat still. And potentially once that retreat gets underway and if the ice flow starts to retreat and they go into an over-deepening, we get closer to dynamic thinning occurring, we might start to see acceleration in those glaciers as well. But looking at climates, we see that retreat is very sensitive to seasonal climate changes, particularly temperature. So we're seeing seasonal consistency between monthly temperature and monthly retreat and monthly temperature, and the same with precipitation. So high rates of precipitation on a monthly scale and higher temperatures on a monthly scale drive high rates of retreat, which is not too surprising. But interestingly, when we look at the trend in retreat and annual rate of retreat and velocity, we find a strong correlation between annual ice velocity and reduce annual ice velocity trend and reducing rates of retreat. So basically glaciers that are less sensitive to annual change in ice velocity have accelerating rates of retreat. I find it quite hard to get my head around these stats sometimes, but I've only just picked them back up today, so it's difficult to get your head around sometimes, but some interesting correlations nonetheless. This is sort of early work as well, so just pulling these out and be interested to hear your thoughts. But yeah, that's pretty much it from me. And yeah, open to any questions.
Awesome. Great talk, Alex. And we have plenty of Zoom applause here. And now I just open the floor to any questions we have. I know we've had a few in the chat as well. So yeah, if anyone in the audience has a question for Sonam and or Alex.
There's one actually about the ice dim lakes. Okay. Can I go ahead? Okay. Thank you. I don't know if I'm pronouncing your name correctly. Trevor, is it like that? Thank you, Trevor, for your question. Yeah, in Bhutan, the we do not in Bhutan we do not have like large ice dam lakes, but there are substantial number of superglacial ponds, and definitely they also pose downstream global danger or risks to the downstream settlement. In fact, Bhutan experienced one glacial lake outburst flood originated from superglacial pond, which actually washed away several bridges, and even it prompted evacuation in the downstream as far as around 60 to 70 kilometer downstream of the lakes. So yeah, I forgot to mention the year that was it was in 2010, but the danger or risks from those superglacial ponds are very least known. There are always more don't know than the what we know. So I have a feeling that the popular susceptibility, the glove susceptibility approach we use for proglacialics might not be applicable for the superglacial ponds because of different geotechnical settings and other factors. We really don't know the subglacial hydrology. So yeah, that is a lot of uncertainty. But yes, they do pose the glacial lake outburst flood danger to the downstream settlement. Hope I answered their questions.
Well, thanks, Sonam. Yes, it's very interesting. I mean, I find it surprising that you have not seen any ice dam lakes. Is it because there's a subglacial waterway that goes all the way from the top of the glacier to the bottom of the glacier, so a lake cannot form? I mean, I think it is very surprising that there aren't any.
I don't have a definite answer for this, to be honest. Yeah, I haven't seen the big ice dam lakes in Bhutan, but yeah, they do have.
Have you gone to the tops of the glaciers?
I have been to only one glacier actually that do have a lot of actually super glacial ponds. Yeah.
Right. And the superglacial lakes, when they collapse, do they leave a moolah in the ice?
Excuse me, can you say again?
When a superglacial lake collapses,
Yeah.
does it leave a moolah, a shaft, going down in the ice?
Uh, Yeah, I feel like the Bartley's the 2010 glove was actually caused by that type of mechanism actually, like
Oh,
superglacial pond drained into the glacial conduit and then it got like it was the drainage the lake that got drained was actually located right in the middle of the glacier, but the actual outburst has happened from the trunk of the glacier. The
right. The water came out at the base of the
yeah,
glacier.
yeah,
Yeah.
yeah, yes, yeah,
So
yeah.
that's what I would expect an ice dam lake to do as well.
Yeah, yeah. So yeah, I think there are numerous actually small ice dam lakes. I think some of them are combining, merging, and forming like a pro-glacial lakes, and yeah.
Okay, thank you.
Thank you.
Maybe I could add to that actually, because when we looked across the whole Himalayas, we didn't actually find any large ice dam lakes that were that significant, like really big ones. But just down the valley from where we're working in Bhutan, there's two glaciers that have a lot of superglacial lakes on the surface that are evolving and growing, emerging, as someone was saying. So yeah, that provides a different mechanism to flood risk in.
It looks like co-host Alan has a question.
If no one else has one, I'll jump in. I'm curious, um, obviously this research has a lot of implications for people living in these mountains and downstream. And I'm curious how your research questions have been kind of explicitly shaped. Like, has it been mostly based on like data availability versus, you know, will a particular type of experimental design lead to particular decision making in a certain way? So yeah, I'm curious how the utility of the research drives the questions you're asking versus other factors that might drive the research that you're doing. And that's yeah, both for Sonam and Alex. So I don't know who wants to speak to it first if it makes sense to you.
I'll go first on that. Yeah, so we we were starting. I sort of signed up to this Bhutan project and I wasn't really sure what to look at. And then it was good. Lunan actually turned out to be a great place to focus the initiation of this ice velocity dynamics. And it was actually probably a great case study in terms of looking at very close neighboring glaciers, but we saw massive variability in terms of retreat. And that's sort of what inspired my project to evolve to looking at the rest of the Himalayas, because it seemed like a logical route to, if this method works here, then why not expand it to the whole Himalayas and then see what we can get out of that in terms of expanding data and drive some interesting statistics from that. So yeah, that's what I'd say to that question.
Yeah, for I think it's actually I what to say like the main motivation is obviously like if it is something that can really make difference at the community level. So that's partly why we use this approach to define dangerous glacial lakes by combining both hazard mapping and the downstream settlement. And it is also like now there are like thousands of glacial lakes, and it is difficult. It is definitely not possible to do mitigation for all the glacial lakes. Uh, we can't like monitor all the glacial lakes because of these logistic challenges and all. So if we, for example, identify like one downstream area, like for example, here we have identified one like area called in like in Paro district, like Paro town. So now it is affected by numerous glacial lakes, but if it is monitored, then if like if you can place a early warning system in particular area, which can cover all the glacial lake that can likely drain into this particular area, then also I think that will really ease the mitigation mitigation in terms of cost and logistic. We are actually working closely with our country partner as a broader this glacial lake outburst flood project we are taking at our university and trying to actually really communicate our result with them. And yeah, we are actually really looking forward that it can be really useful to the like people and the local leader in Bhutan.
Great, thanks so much.
Looks like we have another question. Is it a Gargi?
Yeah, hello. Am I audible?
Yes.
Yeah, I have a question regarding the monitoring system. Like, could you briefly explain like what type of sensors and monitoring technologies you used and how the data is collected and transmitted for analysis?
Yeah, this monitoring is, as I mentioned earlier, so we are actually doing one like a dedicated glacial lake outburst flood project in Bhutan. So our key focus area is Lunana, and we are particularly monitoring Tortormitso, which we have identified as the most dangerous glacial lake in Bhutan. And it is also actually identified as most dangerous glacial lakes by the previous studies. And so, yeah, we have actually various sensor installed there. Like we have time-lapse cameras, we have seismometer, we have water level sensors, and we have also a LiDAR, we call light box. So yeah, data in terms of data transmission, it is very challenging actually. We have a Sterling infrastructure set up there, and we were able to do data transmission for like for 1 month or so, and then it got disconnected. So in terms of logistic, it is really challenging. But we also are working with the local people there, so and we have actually assigned actually last time we have assigned one of the school teacher there to help us download our data from the sensor and send to us. So he did it quite a few times, but now he's also no more in Lunana. So that's quite a challenging, but we are really enhancing our collaboration so that even if we can't do live streaming of our data, so we should be able to at least have somebody at the site who can download data for us. But yeah, logistically, it is really challenging actually.